In this video, I want to go through an example that was posted on the discussion board. It's a really great question about how to find a marginal distribution when the integration bounds include infinity. Okay, so this was the example that was given in the discussion board. However, there's a problem with this example. We can't find the marginal distribution when the original function is not a probability distribution function. Okay, so this is not a PDF, okay, and it's not a PDF. What does that mean? Why isn't it a PDF? Well, remember, not any function can be a probability distribution function, right? A probability distribution function has a very special property wherein the, if I were to integrate over a probability distribution function, if I were to integrate over it with regards to x and y, I should get 1. Okay, and it's a very important property. We should never forget it. Okay, so if I integrate the total area under the curve, or the total probability should equal 1. So since if you were to integrate this, you would not get 1. This is not a PDF. Okay, and actually, I think you were starting to notice this when I was reading through the discussion board. It looks like you were getting infinity. Right, you're getting an answer when you were integrating over f. You weren't getting your answer was included in an infinity term, so that's not okay, right? It should just equal 1. All right, so let's change this up a little bit, and let's talk about a probability distribution function. It still has the bounds of our integration are still going to include infinity, but this is a probability distribution function. Okay, so meaning if you were to integrate over it, you should get 1, and you would get 1, right? Okay, so I want to find the marginal distribution fx. I want to find the marginal distribution for x. Okay, so if I'm trying to find the marginal distribution of x, then I should integrate over y. I should take the joint distribution and integrate over y. All right. Now, when I'm doing this, I can break up this integral, right? Just like how you can break up areas under the curve using the addition rule for integration. So I can break this up from negative infinity to 0, then from 0 to infinity. Okay. Now, when y is between negative infinity and 0, meaning y is less than 0, then we're in the other y situation. So this function is just 0. So if you integrate 0, then you get 0. So this basically goes away. That's 0. Okay, this is the more interesting side over here. When y is between 0 and infinity, then we're up here, where f is 2e to the negative x minus 2y. All right? So this is what I want to integrate. Okay, so the question is now, how do we integrate this? Okay, we have this infinity up here, so we have to think about this carefully. I'm going to go ahead and rewrite this. So I'm going to rewrite it here: 0 to infinity, 2e to the negative x minus 2y dx or dy. I'm going to go ahead and use U-Substitution to do this integral. You don't have to. If you want to just figure out what the integral is right away, you can do that. I'll go ahead and use U-Substitution though. So I'm going to do u equals negative x minus 2y. So du, taking the derivative of u with regards to y, because remember this, we're integrating over y, so x is just a constant, so that goes away. We get negative 2 dy. Okay, so du divided by negative 2 equals dy. So I can go ahead and plug this in for here, right? This is what U-Substitution is for integration. So I would have, so this 2, now this is e to the power of u. Actually, I need to rewrite those bounds. So I'll do that here in a second. Okay, so I have 2, that's this 2, e to the power of u, right, because I just plugged in u here. dy is now du divided by negative 2, okay, and the negative, and these guys cancel, and we're left with negative e to the u du. Okay, I had to erase the bounds because I'm no longer going from 0 to infinity. Rather now, this was for y equals 0 to y equals infinity. Now I have u equals, let's see, if I plug in 0 for y, I get u equals negative x. Okay, so if I plug in 0 for y, then I get u equals negative x. To u equals, if I plug in infinity for y, see, I would get negative x minus infinity. That's basically negative infinity, right? Whatever negative x is, it's so small compared to whatever we're minusing infinity. So that's negative infinity. So my integration bounds then are from negative x to negative infinity. Okay, so now let's go ahead and do this integration. So if you integrate negative e to the u, you get negative e to the u. And our bounds are from negative x to negative infinity. Okay, so now I know I'm about to be plugging in negative infinity here for u, and I'm going to subtract off. I'm going to plug in negative x in for u. Okay, and let's see. I have negative e to the negative infinity. This is, when you have a negative exponent, this is the same thing as e to the positive infinity, right? That's what negative exponents are. It's basically on the bottom of a fraction. Okay, this negative and negative makes a positive, so this is e to the negative x, which I could have written as 1 over e to the positive x. Okay, so now I have e to the infinity. What's that going to approach? This is going to be a huge, huge number. It's basically infinity. So I basically have 1 over infinity. What's 1 over a really, 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 really big number going to approach? It's going to approach 0, right? So this basically is 0 plus e to the negative x, okay? So this is basically e to the negative x, all right? So when you're plugging in infinity, it's basically like you're finding a limit as x is approaching infinity, okay? Or in this case, as u is approaching infinity, all right? So you can think of it as like finding a limit. All right, so I'm not quite done. I still need my support, right? Never finish writing your marginal distribution without also having your support. So this is my marginal distribution, and my support would be x must be greater than 0. 0 otherwise, okay? And this is my marginal distribution.